you guys for the first part of the video lesson or group of videos that we are posting on the wave nature of the light. We saw reflection. And what was happening during the reflection, the light was traveling on the same medium. So if it was air, then it was traveling into air, or if it was glass or anything. So as the light was traveling, and then we saw the mirrors, the medium in which the light travels was not changing. It was the same one. But when the light is traveling into two different mediums, then the phenomena that we deal with, or the way, what do we call that phenomena, is a refraction. So what is happening is that we have two mediums. So it's medium 1 here and medium 2 that are divided with like a surface. Medium 1 can be air, can be glass, can be diamond, can be anything, and medium 2 as well can be anything. Now, what do we notice as the light is traveling from medium 1 to medium 2? This is the incident ray with a certain angle, that is the angle of incident. It is refracted into medium 2, and this will be the refracted ray in medium 2, and this will be the angle theta 2, which is known as the angle of refraction. Based on the configuration, so this is what is happening when it is traveling. Refraction. Based on the configuration of the way that the ray is traveling into different mediums, we can even draw the conclusion of that is known, the index of refraction. What is the index of refraction of medium 1 in comparison to the index of refraction of medium 2? So now, what is the index of refraction? Actually is the ratio of the speed of light in a vacuum with the speed of light on that particular medium. Speed of light on vacuum and the speed of light on that medium. Then this is known with the lowercase m. Now, the speed of light in medium, in a vacuum, is 3.0 times 10 to the power of 8 meters per second. And we have said, or we are accepting, at least for now, that this is the highest speed in the universe. Okay, it's the highest speed on the universe. Now, when we know that the index of refraction has a value, then we can draw the conclusion based on what is the index of refraction, that this is never less than 1. Okay, so index of refraction is always greater than or equal to 1. The case of that it is equal to 1 is when the light is travel, or the ray is traveling into either air or vacuum. We consider even air as the light traveling with a speed of 3.0 times 10 to the power of 8 meters per second. Let's see, based on this information that we have here, how can we calculate the speed of light when we are moving into a glass that has an index of refraction of 2.32. And another thing that I want to add into it is that the index of refraction doesn't have units because you are dividing meters per second by meters per second. So the index of refraction doesn't have units on it. So on this case, the index of refraction is 2.32, and we are looking for V, and knowing or using the fact that the speed of light is 3.0 times 10 to the power of 8 meters per second. So now, based on the fact that the index of refraction is the ratio between the speed of light in vacuum and the speed of light in the medium, we can figure out that the speed of light in that medium will be whatever is the speed of light in vacuum, that is a constant, over the index of refraction. So in our case, the speed of light on that particular glass will be 3.0 times 10 to the power of 8 over 2.32. And in your calculator, you can figure out that 3 times 10 to the power of 8 divided by 2.32 will be equals to 1.29 times 10 to the power of 8 meters per second. So as you see here, the light travels slowly into this particular glass with the index of refraction of 2.32. Now, the index of refraction is something that it is for a specific material is a constant value. So we consider that the index of refraction of air or the index of refraction of vacuum is 1.0. But then usually the index of refraction of water is considered to be 1.33. And then it goes into different index of values for the index of refraction until it reaches, let's say, diamond at 2.42. You're not supposed to memorize those numbers. You are just either will be given on the question or you will use a table that will be provided to you. Now let's figure out now, okay, we have a new phenomena. What do we have to do? How can we manage this? And now, surprise, on everything that we are doing in science, every time that a new concept is presented to you, then a new or bunch of laws and information are given to you. Now, when we are dealing with refraction, as I said, we have a situation that looks like this. So let's suppose that we have here medium 1 in which the index of refraction is N1 and the light is traveling with a velocity V1 and the light has a wavelength of lambda 1. And in this surface where the two mediums are kind of in between each other, then we have medium 2 that has an index of refraction N2, a velocity V2, and a wavelength of lambda 2. So now when the light is traveling starting from medium 1, the ray that is coming toward the surface that divides the two medium is known as the incident ray. And the same as in reflection, the incident ray is forming with the perpendicular to the surface an angle of theta 1, which is known as the angle of incident. So this one here is angle of incident. And as it is passing through from medium 1 to medium 2, the ray is deflected. Okay, it is forming now with the, this is known as the refracted ray, and it is forming with the perpendicular an angle of theta 2, which is known as the angle of refraction. Now, as it is passing through those mediums, the rays are following a law, and that law is known as the Snell's law. Snell's law. And Snell's law is saying sine theta 1 over sine theta 2 is equal to lambda 1 over lambda 2 equals to V1 over V2 and equals to N2 over N1. This is known as the Snell's law. Now, what do you have to keep in mind when we are talking about Snell's law is that frequency, which is the other quantity that we discuss into a wave, is not part of the equation. And the reason for it is because frequency is constant as it is moving, stays constant as it is moving from medium to medium. Okay? And the way that we use Snell's law is that we use the pair of ratio that we are interested at. So let's suppose that we have a situation in which, so example 2. Let's suppose that we have a situation in which the object is moving from, or not the object, sorry, the light is moving from air to water with an index of refraction of 1.33. And as it is moving, the geometry of the refraction will be something like this being the angle of incident, which will say that it is equal to 25 degrees, and the angle of refraction is smaller, theta 2, because the N of air is considered to be 1. So if the angle of incident, is greater than the refracted angle or angle of refraction, then N of the second medium is greater than N of the first medium. And the Snell's law, the relationship that you see here, is telling you that. So if you are asked to draw like a diagram, a ray diagram of the light traveling from air into water, then you should draw something like this. And if it is the opposite, then if you are moving from water to air, then the angle of refraction will be greater than the angle of incident when you move from water to air, from more dense to less dense material. Anyway, so now in this case, the angle of incident is, let's say, 25 degrees, and we are looking for the angle of refraction. So the relationship that we will use will be sine theta 1 over sine theta 2 is equal to n2 over n1. Now, sine theta 1 is 25 degrees over sine theta 2, which we will find, and 2 is 1.33, sorry, over 1. So from here, sine theta 2 will be equals to 1.33, sorry, sine, yeah, sorry. So will be sine 25 over 1.33, and sine 25 over 1.3. Make sure that you're closing the bracket. Sine 25 divided by 1.33 is 0.317758, whatever. And the calculator is giving you. And angle theta 2 will be inverse sine of the answer. So inverse sine of the answer, make sure that your mode is in degrees, and this will be 18.5 degrees. So even the calculations are telling us that the mode, the angle for refraction is less than the angle of incident on the case when you are moving from a less dense material into more dense material, from material or medium with the index of refraction that is less than medium 2, from medium n1 less than n2. Okay, let's see more examples on. Let's see a situation now in which we are traveling from a medium that has a higher index of refraction than the other one. So medium 1, let's suppose that is a diamond, and the index of refraction for diamond is, let's say, is 2.54, and this is the first medium in which the object is traveling, and let's say that the index of refraction here is 30 degrees, and it is going into water with index of refraction of 1.33. So index of refraction of 1.33. So now what we will do, this theta 1, what we will do is figure out what is the angle theta 2. So again, to solve this question, we will use Snell's law, which is saying sine theta 1 over sine theta 2 is equal to n2 over n1. In this case, in difference with the previous example, we don't have an air that index of refraction is 1, but we have 1.33 over 2.54, that is the index of refraction for diamond. And now let's replace the angle, so then we'll have sine 30 over sine theta 2 is equal to 1.33 over 2.54. And from here, using the calculator, the angle theta 2 will be inverse sine of 2.54 times sine 30 over 1.33. Using the calculator, we'll find that angle theta 2 is 72.7 degrees. And even the calculation, as I said, tells us that we are dealing with an index, like we are dealing with a wave traveling from a more dense, higher index of refraction to a less dense, lower index of refraction. Okay, let's see a question now in which we are calculating the speed, knowing the index of refraction. And this is why I said that when we see the snail's law, we take the ratios that are interest to our problem. So now let's suppose that we have light that is traveling from air to water. And air, the index of refraction is 1, while water has an index of refraction of 1.33. This is kind of common, so you can say that. And what we are looking is what is the velocity in which the light is traveling into that medium. So the situation, the ray diagram of this will be from air, the incident, into water. So this will be the refracted ray. Now, based on the Snell's law, what we have is V1 over V2 is equal to N2 over N1. So this is the pair of ratios that we will use, knowing that V1 is 3.0 times 10 to the power of 8 meters per second, because it's the speed of light in vacuum or air. And we are looking for V2. So this will be 1.33 over 1. And from here, we can say that V2 is 3.0 times 10 to the power of 8 times 1, which is the index of refraction of medium 1, over 1.33. And when you use your calculator, 3.0 times 10 to the power of 8 divided by 1.33 is 2.26 times 10 to the power of 8 meters per second. And this will be the speed in which the light will travel in water with an index of refraction of 1.33. Let's see further another question in which we are finding what is the wavelength. So let's suppose that we have a wavelength of 850 nanometer that is traveling in air. And as it is passing through diamond, moving to diamond, so this is lambda 1, lambda 2, as it is moving into diamond with index of refraction of 2.42. So now based on the Snell's law, we will use the ratio lambda 1 over lambda 2 is equal to N2 over N1. And now air has an index of refraction of 1. So then we will have 850 nanometers. To convert it into meters, we go times 10 to the power of -9 over lambda 2. You can leave it as nanometer as well. It's fine. 2.42 over 1. So from here, lambda 2 will be 85 850 nanometer divided by 2.42, and that will be 351 nanometers, or 350 times 10 to the power of -9 meters. Both of them will be correct. You just have to look for the units that the question is asking you to.